Hello, welcome to the first video in our next subtopic, which is motion of charged particles in electric fields. This video will be looking at electric potential energy, work, and electric potential difference. The picture is a bit random, I just couldn't think of anything to put here, so I've gotten a picture of MGMT Electric Field. It's a good song, it's off a good album called Oracular Spectacular. I'm not sure if it's a big deal anymore, but it was a big deal maybe 12 years ago. Anyway, if you're interested, check it out. When a charged body moves or is moved from one point to another in an electric field, work is done on or by the field. The electric potential difference between 2 points is the work done per unit charge on a small positive test charge moved between the points, provided that all other charges remain undisturbed. In Stage 2 physics, you're expected to be able to solve problems involving the use of this equation here, which is work equals charge times the potential difference. I just want to point out something here or make a note of. So a test charge is a point charge with a small magnitude such that its effect on the electric field is negligible. So when this charge is travelling through an electric field, the charge due to that point charge itself is negligible. It might be worth potentially just quickly annotating your notes so you know that, just in case it does pop up in any exams. So the electric potential energy is the energy that a charge has due to its position in an electric field. So like a body would have gravitational potential energy due to its position in a field, so the higher, for example on Earth, the higher up a body in space, the more potential energy it has due to gravity. So you might be familiar with the potential energy equals mgh rule. So its electrical potential energy is similar to that, it's just the field, rather than being a gravitational field, is an electric field. Electrical potential energy is a product of the electrostatic force and the distance from wherever the electrical potential energy is zero. So the electrical potential energy is going to be zero when when a charge is at its opposite charge on between two plates. So what that is saying is that the electrical potential energy is equal to the electrostatic force multiplied by the distance from wherever the electrical potential energy is zero. The electrostatic force from our previous videos we know is equal to EQ, so the electric field strength multiplied by charge, or whatever the charge is, and displacement is displacement, so the distance. You might remember this here from last year, because work is equal to the product of force times displacement, and work is also equal to the change in energy. So there might be a little bit of familiarity there. So here we've got three different situations of positive charges between oppositely charged plates. So in this situation here, the first one, the electrical potential energy here is going to be equal to zero, because the charge is at its opposite plate, so the plate opposite to the charge's charge, and there is no energy because the charge isn't going to move anywhere unless work is done on that charge, because it wants to be at its opposite charge because the opposites attract. So electrical potential energy there is 0. In this situation here, our charge has been moved and has a velocity in the upwards direction, and this is opposite to the direction of the electrostatic force. So in this situation, work is done to overcome the electrostatic force of attraction. The electrical potential energy here is going to be equal to the electrostatic force by displacement, which we know is equal to electric field strength multiplied by the charge itself, and then multiplied by the distance away from the opposite plate. So the field is doing negative work on the charge here, and I'm going to dive into this a little bit more later on into the video. In our third situation here, the charge is coming back towards the oppositely charged plate. As it moves back towards the opposite plate, the electrical potential energy decreases and the kinetic energy increases, so the energy due to motion. And this is consistent with our law of conservation of energy. So energy is neither created nor destroyed, but it is transformed between different types of energy. So the potential energy or electrical potential energy is converted to kinetic energy as the charge moves back towards the oppositely charged plate where it wants to be. In this situation, because the motion is in the same direction as the electrostatic force, the field does positive work on the charge. Again, I'll come back to that idea of negative and positive work. So we'll look at work now. The change in electrical potential energy of a charge is equal to the work done by the electric field on that charge. This is related to our equation that we were just using before. So this here is the electrostatic force, and then this here is the distance over which the force is impressed. So what I mean by that is the distance away from where the charge wants to be at the oppositely charged plate. Now work is positive if it's done in the same direction to the electrostatic force. It's negative if it's done in the opposite direction to the electrostatic force. And what this is saying essentially is that by doing the work in the opposite direction, we're gaining energy. So the work that is being done is negative. In this situation, we're losing energy, so the work that is being done is positive because it's in the same direction as the electrostatic force. So moving on to electric potential difference, which is the change in voltage essentially. Electric potential, or volts, is the electrical potential energy per unit charge, and this changes with position in the field because obviously the electrical potential energy is going to adjust depending on where we are in the field. So the electrical potential energy per unit charge is therefore going to adjust, and thus the electric potential. The electric potential difference, which is the change in electric potential between 2 points, is the change in electric potential energy per unit charge. So this is given by this rule here, so electrical potential energy per unit charge, and that's equivalent also to the work per unit charge, and as I said or alluded to, its unit is volts. You might be able to see that if we've got particularly this equation here, we can rearrange potential difference equals work per unit charge to be work is equal to charge by potential difference, and that is this equation here. So we've got an example: an electric field accelerates xenon ions which have a charge of 1.6 by 10 to the negative 19 coulombs. What is the work done by the field if the ions pass through a potential difference of 1.3 kilovolts? So to do this, we'll use the equation that we just figured out before, this one here. Work is equal to charge by potential difference, and we'll just have to fill those in. So our charge is 1.6 by 10 to the negative 19 coulombs, and our potential difference is 1.3 kilovolts, which is 1.3 by 10 to the 3 volts. If we pop this into our calculator, we'll end up with a work amount of 2.1 by 10 to the negative 16 joules. Another example is an X-ray tube that uses an electric field to accelerate electrons across a small gap. What is the potential difference across this gap if 1.12 by 10 to the negative 14 joules of work is done on each electron? Just heads up, if you see this e to the minus, that's just my symbol for electron. For some reason I've written the word electron here. Sorry for the inconsistency, but if you do see that e minus, it just means electron. To work out this, we can just rearrange our work equation, or we can just remember that potential difference is equal to the work per unit charge, or work divided by charge. And we know that our work is 1.12 by 10 to the negative 14 joules, as mentioned here, and our charge of an electron, which we'll have on our formula sheet, is 1.6 by 10 to the negative 19, and that will be coulombs. So 1.12 by 10 to the negative 14 joules divided by 1.6 by 10 to the negative 19 coulombs, and that will give us a potential difference of 7 by 10 to the 4 volts, which is 70,000 volts.